Today's video works with Newton's method. It is a method for how to find the roots of high-degree equations. Imagine you had something crazy like this. We know for quadratic equations we can use the quadratic formula. There are also formulas for third and fourth degree equations. However, if you have something complicated like this, or if it's something like cos x equals x, we don't have any formulas that can solve those things. One thing we could do is we could graph it, and we could kind of eyeball it by zooming in. Or with our calculators, we can get it out to 9 decimal places. Well, what your calculator is really using is a thing called Newton's method to estimate where that root actually is. Because again, there's no exact formula for it. Here's a visual picture of what is going on with Newton's method. And you might want to pause the video and copy this picture down because it is an important one so that you know what is really going on. What we will do is we will always have an initial guess of our root. In the initial guess of our root, we will just look at the graph and see roughly what the root looks like. That guess will be our x1. So in our picture's case, we're saying that this is our guess right here, x1. What we then do is we go up to the graph and find the point on the graph that corresponds to that first guess of the root value. And that gives us some point, x1 comma f of x1. That's just an x comma y. That is the point that is on the graph at the x value that we chose that was pretty close to our actual root. We then do the tangent line. We know how to find a tangent line equation if we know a point, which we now have, and if we know the slope. Well, the slope we can get from just doing the derivative of our original curve. Even if it's a really, really big, high-degree polynomial, we can still find the derivative. We can sub in our x value, and then that'll give us what the slope is. So we can get this tangent line equation. Once we get that tangent line equation, we want to find where the x-intercept is. Well, remember, an x-intercept is always something comma 0. That'll come into play when we start putting the equations together in a later slide. What we've now done is that x-intercept should hopefully be a better approximation of our root. Notice we got a little bit closer. Then what we'll do is we'll just repeat it. We'll go up to our graph, find the point. We'll now do our tangent line again. That'll give us another x-intercept. That point will become x3. We then go up to our graph, do another tangent line. That'll give us another x-intercept. That now gives us x4. And if we keep doing that over and over and over again, in most cases, that will bring us to our root. Now, it is important that we guess something close to it initially, because otherwise, if you're too far away, sometimes it might not send us to the root, or it might send us to a different root if there are multiple roots. So let's look at this equation-wise. So we said we had some point, x1 and f of x1, which was our point on the curve. And our derivative at that point will give us the slope. That's our f prime of x1. So here's our equation of the tangent line for that first tangent line. We've got y minus our y value equals our slope at the point times x minus the x value. Now the thing we want to find is our x-intercept. Well, for any x-intercept, y is always 0. So if we replace that y with a 0, we now just have negative f of x1 over on that side. And the only variable now in our equation really is this one here, the x2. because we really would have numbers in for f of x1, and f prime of x1. Well, if we work to get x2 by itself, you divide that slope over and then add over the x1. So because the f of x1 was negative, we'll end up with x1 minus f of x1 over that f prime, the slope. So really what this is, to find our next x value, our better approximation of the root, this is our original guess. This is the y value of the original guess. And then this is the derivative at the original guess. And another way of saying derivative is it's the slope at that initial guess on our actual curve. And then that can give us our second approximation. Well, to find the third approximation, we just kind of repeat that. To find the third one, we'll now have our second approximation, the y value for that second approximation, and the slope of our original curve at that second approximation. So here's a little picture, a nicer one than the one I drew. Notice they're getting closer and closer and closer to that. And that is the process that we're finding. We're getting x values that are closer and closer and closer to that actual root. So in general, what we have, if we want to find the next approximation, we just take the previous approximation, subtract the y value of that previous approximation over the slope, which is really the derivative at that previous approximation. And we will use this idea to set up our calculator to find this for us pretty easily. And as our approximations become more and more, so as our number of approximations becomes large, we should eventually approach that root. So a limit is saying, what are we getting close to? We should get close to that root. Now, there might be certain cases where it will not converge to the root. So with this one, notice when we pick x1 and draw our tangent line, we get x2. And then if we do our tangent line at x2, x3 sends us really far away from the root. It's not getting us closer and closer to 0. This will occur when we have a tangent line slope that is close to 0. What we could do here is we could have just picked a better initial guess for x1. If we had picked this a little bit closer here, this would have been our tangent line now, and we would have been a lot closer to the root, and it would have gotten there quicker. So that's why we want to graph it and make a pretty accurate initial guess. Like if you see that it's a little bit to the right of, say, 1, don't use 1 as your initial guess. Use something a little bit to the right of it. Use like 1.1 or 1.2. So you want that initial guess, even though you're just eyeballing it, to try and be as accurate as possible, to try and avoid it being sent actually further away from the root. Now sometimes it might even be outside the domain of the function. So maybe our domain was just x greater than 0 here. If we had that same picture we had before, well, this x3 now is not even in the domain of the function. So that would be an example of a case where Newton's method fails. So we're going to do a couple examples now of how to actually find the root. For this one, they're only asking us to go up to x3. So we need to know what x1 is, which is 2. We'll find x2, and then we'll find x3. Well, remember we saw a second ago that x2 should equal x1 minus f of x1 over the derivative at x1. So our f of x is just that original equation, x cubed minus 2x minus 5. And our derivative of this we have is just 3x squared minus 2. So to find x2, that's going to equal x1, which we said was 2, minus our y value at 2. Well, if right here, if we plug in 2, we'll have 2 cubed minus 2 times 2 minus 5. Well, that's going to be 8 minus 4 minus 5. That'll all give us negative 1. So we'll have minus 1 on top. And then our derivative, if we sub it in, 2 squared is 4. 4 times 3 is 12. 12 minus 2 is 10. This will really become a plus. So x2 is really going to be 2.1, or 2 1/10. 2 was our initial guess. 2.1 is now our x2. If we want to find our third approximation now, x3, we need to do x2 minus f of x2 over f prime of x2. So we have x cubed equals 2.1 minus, if we do f of 2.1, it's going to give us 0.061, roughly. It's actually not roughly, it'll end up exact. So here's 2.1 plugged into our original on top there. There's 2.1 plugged into our derivative. So our f of x2 is 0.061, f prime of x2 is 11.23. And this will give us that x3 is approximately 2.0946 or so. Okay, so that's getting us a little bit closer to our root. And in this particular question, that's all they wanted us to find. They wanted us to find till x3. They will usually either tell you which approximation to find or say it needs to match up with the previous one to a certain number of decimal places. Like it might match to 7 decimal places of accuracy or 9 decimal places of accuracy. And we will see ones like that. So here's a picture of this. Of what we just did. Like I said, we might want to get to a certain amount of accuracy before we give up. We might not have a set number of ones to do. And the reason that sometimes is important is because different people might pick different initial guesses. So it might take more trials, more times doing Newton's method in order to get to the same result. So if we get out to 8 or 9 decimal places, you can usually stop. But again, all the questions I think that we'll see will tell us actually where we're going to stop. Because we're doing the same process over and over again, this is called an iterative process. Because of that, we can do this pretty easily on the calculator. What we will show you in class tomorrow is how we can easily store our answer, and then instead of doing each of the individual numbers, we'll do our answer minus f of our answer over f prime of our answer. And the calculator will automatically sub in our previous x1, x2, x3, and so forth right in for answer, and it'll easily find each of our successive approximations for our root. So that is where we will take this next class period. That's all for today's video. We will see you next time in class.